Hi, my name's Paul Marsh, and today I want to talk about multi-threading in Unity. That's quite a kind of scary subject, but really it's an opportunity to make your games run faster. And in Unity, we do have a few options about how we do that. So without further ado, let's have a little look at what I'm talking about. So, threading, tasks, async await, and jobs. These are the main areas that I want to talk about today. So what do we have in Unity? So Unity works in something called a player loop. And the player loop is basically the thing you see on the right-hand side here. And this comes straight out of the Unity manual. So Unity has to do a series of steps in order to render your screen. Part of those steps are things that we're familiar with, like the start and the awake and update methods, all those sort of messages that it has to try and figure out what it needs to do with all its various mono behaviors. But ultimately, when it does all this work, it does it using one thread of a CPU. So this means that if you've got a phone, then you're using one thread. If you've got a huge gaming desktop computer with lots of cores, lots of CPUs, lots of threads, you're not really taking advantage of that additional compute power. So I want to take a look at how we can get some improvements by utilizing such power. So when we look at Unity, we've really got these options. Or these options are certainly very popular options. So we've got coroutines, and they're not really multi-threading. And I want to highlight them because they kind of feel like they are, but really they're not. And I want to explain why. We've got traditional threading, which is something that .NET has had for a long time, and lots of different platforms have this mechanism. And I want to take a look at that, how that works. Then we've got a slightly newer thing in .NET called tasks, and that allows us to build upon threading in a much safer way, and we'll see how that works. And then building upon tasks, there's something called the async await pattern, and we can see how that builds on, as I say, builds on tasks and provides an even safer way, and also I think probably an easier way to understand async await. And then finally, we got the kind of latest offering from Unity itself, which is the jobs framework, and we'll go into that in greater detail. Okay. So let's have a look at some examples. And we're going to start by looking at coroutines. So I'm not going to go through the actual coding of it. I've got that in a different course, but we'll talk about the sort of specifics of what it is. All these different things here that we've got lined up to have a look at. And I'll walk you through them rather than code our way through them. Okay, so let's have a look at our first example. So let's bring up Visual Studio and make sure we can see the code a bit better. So the first one I want to look at is something called the coroutine. And what this is going to do is it's going to go into our start method, and it's going to create a coroutine. It's going to do something seemingly off thread, is what I've called it. And that something is it's going to go in a quick loop. It's going to do sort of 40,000 square root calculations. It's going to do those 5 times in a little loop, just so I can keep the integer numbers down. And then it's going to do that for 5 times. So it's going to do 5 times 5 times 40,000 square root calculations. And it's going to do this in a coroutine. So let's have a look what that actually produces. So let's just tick on the coroutine script. Yeah, okay, and let's run this. So we're getting some pretty good frame rates coming out of this, and eventually we got to kind of finish. So that all seems reasonably good. Okay. So it appears that we've got some kind of multi-threading going on, but actually have we? So what we'll do is we'll look at a couple of things to try and help us see this. The first thing is to bring up the profiler. I'll just drag that into the scene. Okay, and let's just press run again. Okay, and we can see some spikes here. So let's just pause this a second and have a look at one of these spikes. So here's our player loop that we were talking about earlier, our single threaded player loop. And in here, right at the top, taking up quite a significant chunk of time is this update script delay. And here we are, here's our coroutines. And here we have our actual coroutine, do something seemingly off thread. So this single threaded player loop is having to process this coroutine. So that means that we are taking a hit to do this work on our thread. And so we're not really doing things in parallel. What we're doing is we're kind of circumventing the player loop a little bit by not having to do things in an update method, for example. But ultimately, we still are using only one thread. And I'll try and show that another way. So we can just close this off. I'll bring in a resource monitor. So in here, let me try and find Unity. Okay. So it's going to be this one, I think. And then we can move over to CPUs. Actually, I think I can use a different tool for this. Let me just bring up Process Monitor. So I'm using a different tool now called Process Monitor, which you can get from sysinternals. And let me find Unity again. Okay, so what we like to be here. Okay, so we are running. It's not use. So it's going to be one of these Unity X's. These all seem to be the same process ID. So let's grab that. Okay, and if we can find the CPU. View, where's CPU? This one's, there we are, CPU. Okay, so here's our CPUs on my machine, and we are running some CPUs are doing things, and that's fine. We'd expect that on a windowing system. I'll just let that calm down a bit. Okay, so there's not a lot going on there. So let's run this up. We should see maybe one or two CPUs in action. And I think we can probably see this one is probably doing the work. So as you can see, I mean, okay, it's getting through the work. The FPS is fine. It's not hurting us too much in this particular example. We can see we've got a lot of redundant compute power here that we're not taking any use of, making any use of at all. So this is why this isn't a great solution. Okay, so let's stop that. So what can we do about that? So if we go back to PowerPoint slides here, we got our coroutines, and we've seen that they're kind of seemingly independent of our code, but actually they are stuck in the thread, and we can see that. We've seen that by looking at the player loop and by looking at our CPU usage. So what's next? System threading. So this should enable us to gain access to the computer's additional CPU power. But as we'll see, we're not going to be on the main thread anymore, and that's the thread that's in the player loop. If you hear the term main thread, that's really what we're talking about. Sometimes it's called the UI thread. So we should be able to be more concurrent. That means we should be able to run multiple things at the same time, or feels like it's at the same time. Okay, so let's turn that off, and then we can put on threads. Let's have a look what threads looks like. So this is going to be almost exactly the same code. So we've got our start method, and we've still got our do something seemingly off thread. And that's still doing the same kind of amount of work. Almost the same function. But instead of doing a start coroutine, what we're doing here is we're creating something called a thread. And in that thread, we're telling it what function we want to use. And then we start the thread. Okay. And then that runs. Nothing particularly, it's not that different to what we saw with the coroutine. So we've got that started, and let's run that. And might as well bring the profiler in from the get-go. Profiler, bring you down here, start you running, and off we go, threads. Right, so you can see here the profiler isn't showing those big blue scripting spikes. So there's not a lot, in fact, going on here. We're just printing the stuff out, and it's finished. And it's done its work. So it's done the same sort of work, but we're not seeing any kind of damage in the player loop. Okay, so let's try this again with our CPU graphs. So just let that calm down a bit, some gaps. And we run that. And we shouldn't really see anything. Maybe we'll see an additional window, because we're only using one extra thread. And that's it, and it's finished doing its work. So maybe it was this window here was used, and this was the one for Unity, and this is the additional thread. So we're not really seeing any particular additional massive reuse of all these different CPUs, but we're seeing that we are taking some of the work off the main thread, and that's important, that's useful in itself. But let's start looking at why things are a little bit more complicated. So if we go back to our coroutine, you can see this little thing it does right at the end here. So when the coroutine finishes, it says, okay, this game object is just going to be called, renamed from game object to game object, something about the time, and just some counter, just some fluff in there. Now, when we do that on our thread, let me just try and find, I've got so many examples here. Threads, okay. Let me do the same thing here. So get rid of this function for a moment. And we're going to pass the game object in. So we're going to do var game object equals this game object. And we're going to pass that into the thread. My game object. And then just do game object go equals game object my game object. Okay, so we'll run that. So threading is started. Let's start. Oh, got an error already. Semicolons. Come on. So it's doing its work, and then bang. So here's our first problem. Get time can only be called from the main thread. So here's this main thread again. And we can see here that some Unity functions are only based on the main thread itself. So we can't actually use some features. So, okay, we can maybe use a .NET function to get around that problem. So we'll come down here and we'll change that to datetime.now. Okay, so that's roughly the same kind of feature functionality. So let's come back here and try that again. And it's running, and oh, another error. So set name can only be called on the main thread. So the problem here is we can't do this thing. So we can't change the name of the game object either. So you can see that there's lots of features that aren't available to us when we move away from the welcoming arms of Unity. As soon as we break out of that, thinking that we're doing something clever, we're actually getting stuck in some difficulties. And these aren't unusual difficulties of a thread. These are a very typical problem when you come off the main UI thread and you want to try and change something on the main thread. You have to go via something else. And typically that's called a dispatcher, UI dispatcher, but we don't have that in Unity. So we have to have a little workaround for that. So what we do here is we don't pass the game object in at all. We don't need that. So let's just remove that. Remove that, tidy that up. So what we do instead is we call this function called change name, and that has a similar things here. So again, we're still using date time because we can't use the Unity one. So what does change name do? Well, change name just sets a member field called new name, and then in our update method, we just check to see whether we've got something in new name, and if we have, then we carry out that function. The only other thing to look at here is something called lock. Now the problem is when you go multi-threading, it now means that there's potentially one or more threads doing work, and therefore one or more threads might be trying to change this field. And when we know at the moment there's only one thread, but I need to start getting into this mindset. As soon as we move away from being on a one known thread, we have to start worrying about having multiple threads accessing our same pieces of memory, our same bits of data, our same fields. And to prevent that overwriting happening, .NET has something called a lock. And it allows you to lock to some other object, and I typically call them padlocks. And when you're in this lock, what's known as a sort of critical section here, nothing else can get in here. So one call to change names will come in here, lock the object, do the work. If another thread comes in at the same time and this is locked, it can't get in here. It has to wait until this one comes out and then it's straight in. So it would be a last call wins sort of situation. So if I had a name changed to A, another one came in for B, it would immediately change this one to A, and then the next one would come in and then be B. But because it's threading, it might not come in that order. So maybe B comes in first and then followed by A. So this is where threading starts to become a lot more complicated. But anyway, let's see if this thing works. This little workaround works. So let's save this off. Come in here, back to Unity, and then run. Let's see if our game object changes name. So it's doing some work. And then you can see here that the game object has indeed changed name. So hopefully you can see from that that threading gives you the benefit of doing things away from the main thread. But as soon as you start using that benefit, it also brings a lot more responsibility, the things that you have to worry about. not only to avoid having errors, but also to avoid having strange memory corruptions and things that go on, which is not something you really want to have. Very painful to sort out. Okay, so that's sort of the threading side of things. Let's go back to the slides. So you can see that those threadings have given us the ability to access more compute power. I only created one thread. And we'll see in a second what happens if I create more threads. We'll have a look at that. We've also seen the problems you have when you're not on the main thread. So whilst it's an advantage to go away from the main thread, it also has all these different responsibilities that you have to worry about. One thing I haven't mentioned here, the context switching, that is a problem where if you had too many threads going on, then there is an overhead in managing all these threads, as the CPU has to move between all these different threads to sort out who's doing what. So, yes. So before we go on to tasks, let's have a look at multiple threading. Okay, so I'm going to look at some multiple threads here. So